He's here. I think there's another one over there. Yeah, there's this one. Okay. Okay, that's fine. What's the password? Okay.
I turn it off right now. So
No, of course. No worry. Yeah. Hello, everyone. So let's start the Thursday's day, like for the conference. But before the invited talk, let me give two announcements. So first, after this session, like this invited talk, we have a group photo. We figure out where we're going to do, probably outside, but we'll decide from here until then. And the second announcement is at 12:30, we have the business meeting in this room. So we can have a quick lunch, and then people who want to come, like we present the statistics of participation, submissions. We have a part for discussions, about like for the community to give their opinion on some of the choices and some how TQC should continue. So it will happen from 12:30 to 1:15, I guess, 1:20, yeah. So yeah, please come if you're interested in joining it. And now let's switch gears to the first talk of the day. So we have Zhengfeng Ji. He has had very seminal results in complexity theory and cryptography, and he'll tell us about quantum graphical models.
Okay, so thank Alex for the introduction and thank the organizers for inviting me. My name is Zhengfeng Ji, I'm from Tsinghua University. The talk today I'm going to talk about is forward and backward mappings for quantum graphical models. It's basically a mixture of both a survey of results that I'm reading recently, and also some of my own results. And because the more I read, the deeper I read, the dig in the literature, the more I found the relevant work. So maybe I still have important papers that I didn't mention, but I should. But also, given the time constraint, I select a bunch of work that related to this topic. Quantum graphical models is a fancy name. And before that, you have to understand what is the classical. The classical models are called probabilistic graphical models. And I guess you all have heard about it. They are unified frameworks for modeling complex conditional dependency among data. Very powerful tool. And there are two flavors. One is called direct graphical models. So like the graph on the right, you have arrows between the nodes, and the arrows are modeling the conditional dependence. For example, vertex D has parents A and C. So once A and C is given, then D is independent of the rest of the nodes. And because of this independence information, you can write distribution among the P, A, B, C, D as a factored form. There's also another model called undirected graphical models. And in physics, it just describe the distribution called Gibbs distribution. And also people call it Markov random field in some areas. And in that situation, it's a product of compatibility functions. So you just have a product form where the distribution P, A, B, and C, D equals to some local functions, like for example, phi A, B, depends on the function, depending on the variables XA and XB, and phi A, C, and phi A, D. According to this graphical representation, you have a factorization of the probability. And these are two major graphical models. And the tools for reasoning about uncertainty and to dig out the dependence on data. And it's obviously an important area for data science and machine learning. And I give a reference here, which I found very useful by Wainwright and Jordan from 2007, called Graphical Models, Exponential Functions, and Variational Inference. So as I said, there are models for modeling conditional dependence. And in the case that we are most focusing on is the undirected graphical models. You can consider different type of Markov properties defined by the graph. One is called global Markov independence, where basically if you have regions like A, B, and C, and if all passes from A to B must go through C, or otherwise, if you remove all vertices in C, then A and B are not connected. Then you have the condition dependence. Given C, A and B are independent. And also there's a weaker version called local Markov independence, where you would only require that maybe for a vertex, given all its neighbors, then the vertex is independent of the rest of the nodes. It turns out that these two conditions are equivalent for positive distributions. Interesting result to know. And more importantly, there's a famous theorem called Hammersley-Clifford theorem. It says that the two things that we consider so far, one is factorization. You have a distribution, you can factorize the distribution according to the graph. And the other thing is the Markov property. You have two equivalent Markov property. They are equivalent. So if a graph is factorized, then they have the Markov property according to the graph. Otherwise, if you have a Markov property for a distribution according to a graph, then you have factorization. So it's if and only if condition. And I guess it's one of the most fundamental results in classical graphical models. And we will see that the quantum case is much more complicated than this. And there are a lot of interesting problems and algorithms that people care in this area. We can roughly group the problems into three different areas. One is called inference problems. Basically, you know the model, all the parameters that you need to know, and you want to learn about the properties of the model. For example, you want to compute the marginal distribution. You have defined a global distribution. What is marginal distribution? The second type of problem is to learn the parameter of the model. You don't know the model. You know some observations about the distribution. Then you need to learn the model, the parameter of the model. The third one is sampling. You have a model which defines a distribution. Can you sample from that? Right? And we are mostly focusing on the first two questions, inference and learning. So inference is to learn properties about a given model, and learning is the other direction. There are a lot of algorithms that if you look at the textbooks on this well-specified area, there are many interesting algorithms. Maybe you have heard some of them: Markov chain Monte Carlo, Gibbs sampling, sum product, belief propagation, junction tree algorithm, mean field algorithm, variational inference, iterative scaling, EM algorithm. So we will maybe talk about some of them in this talk. And this unified framework has found many interesting applications in machine learning, statistics, and many-body physics because of the connection. Gibbs state is the thermal state in physics. Now, the quantum version, right? We have talked about purely classical models. What are the quantum models? There are actually different definitions, and the model that I focus on generalizes the undirected graphical models. So basically, there are quantum Gibbs states we are considering, and so you can consider you have a Hamiltonian, and EAs are maybe polys, and you have parameters theta, real numbers defining the Hamiltonian, and then the Gibbs state we will write it as rho beta theta. Beta is inverse temperature. And it has a form 1 over z and an exponential form, exponential minus beta h. So at h has a parameter theta. And z here is it's called partition function. It's just a trace of the exponential. So to normalize the state. Okay, it's all clear. Why is that called graphical models? You can think of it's a generalization of the factorized distributions of this form into this new form, where this capital phi AB now is an operator, not a function, it's an operator. It's acting on system A and B, and operator A and C, and A and D. So classically, these are functions, they're positive functions, give you values that are non-active. In quantum case, I have positive semi-definite matrices. And this circle product generalizes product. In the classical case, there's a very natural thing to do. Multiplication, there's only one natural choice. In the quantum case, because of the non-commutativity, right? You have many different choices, and the circle product is just one product in this form. So two positive matrices M and N, circle product equals to the exponential of the sum of the log. Okay, so you can see like why this is connected to the Gibbs state. Usually this you can think of this phi AB is just the exponential of local terms and take the log and take the sum. This will give you the Hamiltonian as a sum. But this is not actually the only definition. You can have other definitions. Actually, in this paper, quantum graphical models and belief propagation by Leifer and Pauling, they have considered other definitions of for the product. But we are focusing on this circle product in this talk, and focusing on the Gibbs distribution because I think that's most relevant in physics. And we said that classical models are powerful for modeling independence. The Markov properties are very essential for classical models. So how about quantum, right? We can define the quantum conditional independence using conditional mutual information as AC B. This is just a condition that we know that this quantity is always non-negative. This is a consequence of the strong subadditivity theorem inequality. And when this mutual information is actually exactly zero, then we say that it's a typo here, right? We have to say that it's A and C are mutually independent given B. There are consequences having this condition. For example, you have decomposition of the state given by Hayden et al. The equation I listed here is due to Maribus-Ruskay, who proved that for states satisfying this Markov condition, you actually have this funny equation in terms of operators. The log of rho AB is just rho AB is density matrix on AB. Take the log and think of this as an operator on ABC. Because like if you think of this and this is as an equation in one dimension, it's a number, right? You have entropy, it's zero. This is operator equation. So it's a very interesting result. But like we can define a Markov condition, but when you consider a graph and form a Gibbs states, unfortunately the Helmsley-Clifford theorem will not hold in general in the quantum case. If the state is Markov, then it is also factorized in the definition that we gave the circle product, but not vice versa. Like you can easily come up with Gibbs state that are not Markov. So that's a problem in the quantum case. But recently there are progress saying that even though this theorem doesn't hold exactly, they are true in the quantum case in a certain sense that if you consider regions like given ABC regions in this form, if E and C are very far apart, then the mutual information goes to zero with the distance, the R, quickly. So it's a very recent result by Kurahara. I think like this is, I don't know, like maybe people realize this before. This is related to many of the algorithms that we discussed that appeared before this results have been formally proved. So the main message is that quantum Gibbs states they are not Markov, but if you have a large so-called Markov blanket where the neighbors, you choose a very large neighborhood, then you somehow recover the independence. Okay. Okay, so that's basically the setup, and finally I can tell you about the other part in the talk, forward and backward mappings. So we have a model, a Gibbs state, defining the Gibbs states, and the forward mapping we are talking about is when you're given theta, you have all the information about the Hamiltonian, and you compute the local average values of operators EA on this state. So it's just the mean value of EA respect to the Gibbs state. So because we have, for example, m different thetas, and you take the average values, you have m numbers, and at least the dimension match, and under very mild conditions, the mappings between the model parameter theta and mu is 1-to-1. So the forward problem is just given theta, compute the local average values, and the backward problem is given mu, can you find out the model parameter theta? Right. I've called this backward problem learning in the previous slide, and forward problem inference. So it's like two different names for the same thing. So that's the forward backward mappings that we're talking about. Okay, and you may wonder, like, why would you do this, right? Actually, there's a lot of background that I find interesting. And I'll put it into a convex analysis framework. So we can write the Gibbs state here in this form, where this a theta is just the log partition function. We write the normalizer into this. It's a number depending on theta into exponential, and we've defined a quantity called free energy minus t log z. So it's a function of theta because z depends on theta. And you can do a very simple calculation and find out that the gradient of f, the gradient of the so-called Helmholtz free energy is actually a vector of EA average value. So in that sense, so nebula F is the forward mapping. Okay, but you take the free energy, take the gradient, then it gives you the forward mapping. We will give some notations. So we call mu and theta coupled if they satisfy this condition. So these are the defining conditions, right? You have this conditions. You have, if you think of theta as variables and mu as known, then it's a set of m equations of m unknowns. And we define m called realizable mean parameters. It's all the mu's that there is a theta coupled to it. Okay? There is a model so that the local information is exactly mu. Okay. So that gives us the forward direction. So you have given theta, you can compute mu by writing it as the gradient of that. You can use duality in convex analysis, and you can actually write out what is the backward mapping. So because we know that log partition function is convex, and therefore minus t log z is concave. And by the standard methodology, we take the conjugate. Because it's a concave function, we take the inf, the linear term, and then minus f theta, and switch the variable theta to mu. We get the conjugate f star. Okay, it's a very general result from convex analysis that if you have convex functions, f and f star defined in this way, then their gradient nebula f and nebula f star actually are inverse to each other. Okay, and we can write f because they are due to each other. F is actually the dual of f star. Okay, so that's taken from convex analysis in a very general sense. Now you wonder what is this function, right? F star. If you do a calculation, it turns out to be the entropy function. So entropy comes from the local partition function very naturally. You take a dual. So f star is a function of mu, and mu is now in some feasible mean parameter set m. If mu is in the interior of this set, then you can compute from mu the parameter theta. From theta, you define the Gibbs state, and this function is actually the f star is actually proportional to the entropy of rho. If it's not in the closure, then you define it to be minus infinity. So it's almost the entropy function with certain trick to make the analysis better. The last piece that I want to talk about in this convex duality picture is this very famous Jen's principle, the maximum entropy inference principle, that you have like we have the situation we have here, like have local information about system, and you don't know what the state of the system is, and the maximum entropy principle says that you just choose the state that has a maximum entropy. And there are some known structural results about this maximum entropy state. First of all, if you consider two families of states, one is called linear family, the family of states that has exactly the local mean values depending on the mean vector mu. And also you can consider the closure of the exponential family. You take a theta and you form all the Gibbs states and take the closure. So these two families, L and E, they intersect at exactly one point if they are not empty. Okay, moreover, like because it's in an intersection, you know there's a state, the optimal, the maximum entropy state will take this form. It's a Gibbs state of certain unknown parameter theta, and the local matches mu. And based on this principle, or these two results, it's very easy to rewrite the variational formulation of f. We have derived this first part last slide. Now, because of this analysis, you can also write it in this much nicer form, where the inf is now taken over all density matrices. This is an energy term in mu and theta, and this is an energy term in terms of state and Hamiltonian. And we said that this f star is actually an entropy function, right? So it's minus t entropy of the state. Okay, so this is a very useful form that we will revisit later on. So it's give us a variational formulation of the quantity that we care about. So now we talk about the forward and backward mappings separately. So the forward mapping is the inference part, like given the model, what is the local information. And the forward mapping is gradient of f, and it's given by the average values of the operators. So actually, it's known to be a very hard problem if you want to compute this exactly. It is sharply complete in this two papers. It didn't show exactly this problem, but it's a related problem that we know that are equivalent. So exactly, its computation is very hard. And then people consider what is the problem complexity of approximately computing these quantities. So actually, in this paper, a very recent one by Bravi et al., they defined many more problems, but two are relevant here. One is called quantum mean value problem. So you given the model, you want to compute a parameter nu up to some error epsilon. And they also consider a quantum partitioning function problem, just approximate z up to some multiplicable error. So they show that these two problems are equivalent, which is not hard to show, but it's important to know. And these two problems are examples of a very large class of quantum counting problems that are known to be equivalent. And but we don't know what are exactly the class of these problems that they are complete for. But we know that even observation is hard because the classical problems, what we know, like for example, we know that in the counting of Stokemeyer theorem, it's algorithm B to the NP. So we don't know better algorithms. So basically, these are hard problems, but the approximation versions are not unlikely to be sharply hard, but still hard. And given this information, we have to resort to either you consider a very special instance. You cannot consider the general problem in the most general form, or you can relax your condition. You consider some heuristic methods. You don't have a guarantee, but it works well maybe in practice. So that's two approaches that people take. What the first important special instance is that in the classical case on trees, these problems are very easy, and you can even have a linear time algorithm for solving this problem. For example, you could consider a chain graph, and if you want to compute the marginal, for example, the p x1, and you know that the distribution is factorized, so you just need to sum over x2 to xn for this distribution, and you can reorganize the sum so that each time you will sum over, for example, you sum over the last variable, and then this becomes a function of x minus 1. You can do this one by one. So it's a dynamic programming approach to solve the problem exactly. And this method can be generalized to trees. This is for the chain. And when this is generalized to trees, this algorithm is equivalent to the sum product algorithm and message passing algorithms, or as people call it, belief propagation algorithms. So in belief propagation, you have roughly it's like an algorithm where you vertex passes messages, and what the messages are about is what the neighbors think about, what your neighbors think about you, your likelihood of being in some state. So message updates, they have very nice form. So this is a message from U to V. It's a state. It's a function about what V is, right? What the likelihood of V is. So how you update? How do you get this message? It's a summation of over XU, and then this product. So this is why it's called sum product algorithm. This is about what the others think of your neighbors, right? And then you take this compatibility function and multiply them together and trace out the U part. So that's a graphical understanding of this update rule. So the message from U to V is just a summation of a product where involving all the other neighbors and two functions that are representing the compatibility constraints. And the belief is just proportional to the product of all the incoming messages and also the local compatibility function. It may not seem obvious why this is equivalent to the last slide, the dynamic programming, but if you sit down and work it out, it's a very easy thing that you can see that they actually, these two are equivalent. And So this algorithm works on exactly on trees and it's very efficient, but they can also be applied to loopy graphs. So especially when the loops are long, they're not short loops. Because the message passing, if it's a short loop, then the messages go in circle, right? So people can apply it, but then when the graph is loopy, then you don't have any guarantee of how well it work. They may give you wrong answer. Okay, so that's belief propagation. And it's actually related to idea due to beta. It's called beta approximation. So remember that we have written the problem as a so the free energy is actually the minimization problem of a in this form. And really the hard part is to compute the entropy, right, of distribution. So what this is doing is you do an approximation of the entropy according to this very simple rule that you put all the edges entropy together and you minus degree -1 copies of entropy of the local vertices. And you can see that this is called an outer approximation because you also need to, because once you do this approximation of the entropy, all information here is depending on the local information of the distribution. But we don't know how to solve the consistency problem. So you have to relax the consistency problem to a local consistency, not global consistency. Then this problem becomes very easy. So that's how this beta approximation works. It works well in graphs because when you think about the approximation of the Gibbs distribution, actually these two are equivalent. You can use Markov properties to prove that the replacement of entropy with the beta approximation is not a bad choice. And what's interesting is that you can derive the belief propagation update rules, the message passing rules, by considering the optimization problem. And you find out that these rules are actually the Lagrange multipliers of the optimizing problem. So it's a dual picture in the optimization. That's all about classical belief propagation. What do we know about the quantum analogs? Actually, people have studied this a long time ago. Hastings first studies in 2007, and it's called quantum belief propagation. The generalization is very simple. You just take the message not to be in operators, what the neighbors think about your density should be. The rule is just a sum product where the sum is replaced by a trace and the product is now the circle product that we introduced earlier. Unfortunately, this algorithm is not working well even on a tree. If you only know that the graph is a tree, because that Hemsley-Clifford fails in the quantum case. If you know that it's a dual to the beta approximation, and beta approximation is not a good approximation in the quantum case. So people when they introduced quantum belief propagation, they have a modification where you can think of it as sliding window quantum belief propagation, where you have a long window of size L. Where all information about this window is getting propagated. So you can think of it as a blanket, Markov blanket, being long enough so that the conditional Miltonian the Markov party of the chain is approximately satisfied. So why this works much better if you consider a longer intermediate window. There's some recent paper discussing analyzing the convergence. It's very hard thing to do, but people are getting progress along this line. And when Hastings introduced this concept, he proved he proposed a very interesting equation which has been very central to the development of this area. So this is what I would call a quantum Lie propagation equation. It's an expression of the matrix exponential. When you have a matrix exponential where the terms are not commuting, it's not that easy to write down what is the derivative of this matrix function. And he gave a very interesting form. It's over here. So like, if it's all commuting, then when you take the derivative, then the beta and also the thing that in front of the variable v would come down, right? You have a v going in front of the exponential. But now it's the matrices, so it's not that easy, right? Even not commuting, right? So what Hastings provided is a formula of this form. So you should define a variant of V, applying a V, a channel on V. This is like a mixture of unitaries, right? Channels. And this f beta t is some distribution on the real line. And this is just time evolution. This is unitary channels for distribution over unitary channels. So you can think of this phi h of v as some variant of v. Now the derivative is just this variant would come down, okay? And there is an anti-commutator. So you have beta over 2 in front. Okay, that's the formulation, the equation. And the important thing is that this beta, f beta t function decays quickly with t. And it's a distribution centered around a radius of roughly beta, the inverse temperature. So now you can work with together with Leo-Robinson bound to argue that to analyze the behavior of such systems, and it turns out to be very effective for 1D systems where people have found a lot of success, and it will also give us a very simple generalization of the covariance of two operators. So I've given here a definition which I will use later. The covariance of A and B under evolution of H is in this form. So it's the anti-commutator of A and phi HB taking the average value minus A and B average value. So it will give you exactly the covariance if everything commutes. Okay. The other direction we consider like trees, right? And BP algorithms that works well on trees, and there are quantum analogs. There's another direction that people can consider is where you have, if you think about the temperature as an input, right? If the input temperature is very high, then we know that things are much easier. A very recent paper, Akashi, Liu, Motora, and Chan proved that these states are actually exactly separable states, not even close to separable states. Exactly, they are separable states. And so very recent result, we know that the strong correlation decay holds for the systems when temperature is high. So when you have decay of correlations in your system, then the local computations of the observables can become much easier. For example, you can even try to remove a ring of terms at distant L from the observable O that you want to compute. For example, you can consider a function H, which is consists two parts. So B is just this ring maybe, and A is the rest of the terms. So if you remove the B, then the system will be decoupled, right? The inner part and outer part will be decoupled. So for the quantity that we care about, we actually care about H1, right? H1 is the average value that we consider. H0 is just an approximation that we want to use. And you can bound this difference in a very, very simple form. They can write it as the integral of the covariance that we defined earlier. The covariance is a measure of the decay we know that they are decay very quickly. We know that we can bound this term. So you can use this to derive algorithm to compute local densities. And computing local the mean values are exactly the forward problem that we're considering. So this is another instance where you can have high temperature special instance that you can solve. There are also some heuristic methods. The first I want to introduce is called quantum Markov entropy decomposition. It's based on the variational approach that we can write F as optimization problem. And it's very similar to the idea that beta approximation works. You can approximate this entropy function. And in quantum Markov entropy decomposition, the idea is that you choose a neighborhood and you define an order of the spins, and you define the so-called Markov shelled MU as the intersection of the 1 to U minus 1 and the neighbor of U. So this is the Markov shelled of U, so the intersection part. It is unbounded size, right? And you can approximate this entropy as this summation here, which is only depending on a very small region of the system. And then you also need to do some relaxation of the global consistency to local consistency. You derived what is called quantum Markov entropy decomposition. It's classically people consider this, and Pauline Hastings studied this quantum generalization in 2011. They also noticed that because of the similarity, right, of this method to the beta approximation, they can derive some form of quantum propagation. It's a different set of rules how message propagate. Yeah, but it's you can think of it as analog of another form of quantum propagation. Other heuristic methods include mean field approximations. Again, we consider such a minimization problem. We want to minimize. If you want, you can minimize this, then you can compute the log partition function, approximate the partition function. If you consider, for example, the domain sigma to be all the product states, then you know how to compute the energy, right? Product state, and you know the entropy, how to compute the entropy, because it's the sum of the local entropies. So you can easily do this calculation, even though it's a non-convex optimization problem. You can really efficiently solve these problems. And there are also generalization of this method. If you think of the product states as the Gibbs distribution of a vertex, a graph with no edges, right? You can think of maybe a graph like a tree, a subgraph of the graph, which is a tree. Then you can use quantum propagation to do this calculations, and you generalize this mean field method, and it's just called a structured mean field approximation. Okay, so now we will move on to talk about backward mappings, and that's the learning of the model parameters. So the backward problem, because we know that this is inverse, like the nebula of F and nebula of star are inverse of each other. And the problem of computing theta is actually solving the equation, right? You have given mu to compute the theta. It's a very funny equation because this have a high threshold of this matrices, and then divide by the partition function, right? It's a very complete form of functions. But it's an important fact, right? It tells us that if you want to learn the parameter theta, it's faster to match all the local information. Right? There's only one theta that matches the local information. And this is a key observation that utilized in Anshu et al. Result discuss this Hamiltonian learning problem. So the Hamiltonian learning problem is from the different versions. One version is from learning from the Gibbs states. So you have maybe have access to many copies of a Gibbs state row according to some true Hamiltonian, and your task is to find out the parameter theta approximately. I would say this is a related problem to the backward problem, but not exactly. The backward mapping problem, you would only given the parameter mu, but here you're given the Gibbs state. So you are not only given the average value of EA, but other average values of your choice, right? So that's an important fact. And what we know about this Hamiltonian learning problem, which is closely related to the backward mapping problem. First, we know they are sample efficient for local Hamiltonians, and that's result in by Ansher et al. They showed that the technical part is that they showed that the local partition function is theta is strongly convex in the sense that the Hessian has lower bound. But there's a caveat, like the backward problem has intrinsic hardness, which is related to so-called sufficient statistics. Because of the dimension match, they're called sufficient statistics. And even in the classical case, we know that such a problem has complexity consequences. It will be a very hard problem. So people have considered alternative approaches, like when you're given the state row, you can measure other local observables other than EA. So this is what Erwin Tan et al. Come up with. Gave you an alternative way of listing the equations for theta. It's a funny set of equation, the key thing is that you can utilize now a richer set of statistics. What they can show is that actually you can, with an improvement we were recently by Narayanan, the complexity, the time complexity of the Hamiltonian learning problem is at most poly-m, where m is the number of terms or qubits, and there's 1 over epsilon to the O of beta squared plus some extra terms. It's efficient in the sense that the number of qubits dependence is good, but there's the intrinsic hard part where because we are focusing on low temperature case, high temperature case is easy, right? There's extra term that is exponential in beta. That's what we know about this related problems in the backward direction. And even though that's very nice theoretical result, I feel that maybe because the use of algorithmic techniques such as sum of squares converts to some very high dimensional STPs, it's not very practical. If you want to implement algorithm, these algorithms are, I don't think that you can run it on large systems. So what can we do, right? Another thing that what we can do is you can work with the backward mapping problem and using forward mapping as an oracle. So the first idea is you can do gradient descent. We have this formulation of the F star as an inf of mu theta inner product minus F of theta. And if you work out this is unconstrained optimizing problem. You can compute the gradient. You will find that the optimizer actually satisfies the equation that you want. Right? So that means that you can actually minimize this function, compute the minimization problem, and the optimizer of the problem will be exactly the solution to the backward mapping problem. you can use gradient descent method. This is objective function. You do the gradient descent, and whatever you found would be your solution to the backward mapping problem. And so this is in some sense backward mapping reduced to forward mapping. And because if you want to minimize this, then you have to maybe to compute the f star f theta or the gradient of f theta, and they are the forward problem, right? You have current gas, and you want to compute the gradient, and it's exactly the forward problem. So you can solve the backward problem by solving forward problems. This is one idea, and the other idea in the classical literature is called generalized iterative scaling. You can there are different names in this direction. Sometimes it's called GIS, generalized iterative scaling. It's also called iterative proportional fitting. It's called SMART algorithm. And the basic idea is when you have a gas of the parameters and you compute the local densities and you see mismatch and you penalize, it's like feedback to the parameter theta. So this is a quantum version. You can work it with operators. It's maybe look daunting, but it's a very simple update algorithm where in each step you would set the update to delta, which is the log of the ratio between the target value and the current value. And you would only consider that you compute that y here is just the exponential function of the current gas. The condition here, like the caveat, you have to make sure that these operators are not normalized. It's like a POVM. Otherwise, this won't work. So it's a very simple update algorithm. So for example, if you're very lucky that you have all the parameters correct, then this would be mu a, this would be mu a, and this will be 1, and the update will be 0. So you will stay, it will be staying in the same place. So that's a non-commutative version of the GIS algorithm, which we didn't give, but you can easily come up with when the matrices are all diagonal, you have exactly the GIS algorithm. This is also an example that you can solve the forward backward problem by solving a forward problem, because you want to compute this thing. This thing is a forward computation. And you can compare the gradient descent and the QRS. In gradient descent, if you compute the gradient, it's just the difference of the two values. If they are a mismatch, you know how to update them, and you need to choose a learning rate, which is not clear how to do, how to choose that. In QRS, it's much simpler. You just take the logarithm of the ratio. So you don't have to choose a learning rate. And we can prove that QRS converge using a method called auxiliary function method. An auxiliary function is just a function of a matrix and a vector. It satisfies several properties. First, that when delta is 0, this quantity is always 0. Okay, and the second is important. Like we have this algorithm, this updates. This auxiliary function must satisfy that the delta is chosen so that this function is maximized. Okay, by computing the gradient, you will see that exactly you can choose a function so that this is exactly the delta that maximizes this function. So 1 and 2 tells us that actually A is strictly larger than 0 if it's not yet, if there's an error, right? If delta is updated, then you will be like this auxiliary function will be positive. The third property of the auxiliary function is that it measures the progress. So you consider some initial state, and at time step t you have yt. At some step t+1 you have yt plus 1. You measure the difference, right? It's positive. So in some sense this thing decays, right? but it's starting from a finite value. You cannot decay forever, right? So this would prove that this algorithm actually converge. And to prove this inequality, you have to use the a very strong, very interesting inequality called Cullen-Lieb inequality. It has this form, like it's a trace of EA plus B is the trace of EA EC e to the lambda max B minus C. If like B equal to C, then you recover the Gordon-Sampson inequality. But Gordon-Sampson is not sufficient for proving this inequality. You have to dig in the literature and find that there's something stronger to prove this inequality here. Then you have 1, 2, 3, then you can prove actually QS converge. But this only gives you the convergence. What about the convergent rate? How fast this algorithm will converge? And then to talk about this, you can compute the so-called Jacobian of the process. The QIS is an update algorithm. You can compute, like there's some mapping from theta t to theta t plus 1. And you can compute the Jacobian by a theorem due to Ostrowski. The convergence rate, convergence is governed by the so-called spectral radius of the Jacobian. Just like if it's linearized, it's a matrix. If the matrix is shrinking, right, then you're good. So what is this matrix? It's identity minus gamma inverse lambda. So gamma is a diagonal matrix where you have the mean value of the operators. And this is actually the second derivative. This is the first order derivative of the partition function. And the lambda has this very nice form. It's actually using Hastings quantum propagation operator, we can write it in this form. Okay. So the question is then, can we bound the radius of this expression? We have some progress. We haven't finally solved this thing. We can link it this into the answer result where you can give upper bound on the largest eigen value. So because we know that this Jacobian is having this form, and so it's and because this form of the lambda, you can easily prove that it's greater than the Hessian of the log partition function A, and then we can prove that it's at most 1 minus m lambda min L. Lambda min L is known have a lower bound, so you are minusing some noticeable quantity, so it's bounded away from 1, right? The thing that we didn't succeed, actually we thought that we proved it and even wrote a paper on arXiv, and then later on we realized that the proof is incorrect. So what we also need is we want to prove a lower bound because we want to bound the radius, right? You need to prove that the eigenvalues are not too negative. And actually we conjecture that all eigenvalues are positive, even though we haven't been able to prove it. So the conjecture is that these two matrices that we defined on the side, they actually satisfy a matrix inequality. So the second order matrix is bounded by the diagonal first order matrix. If you can prove this conjecture, then we have a rigorous proof that the QIS algorithm actually have a very good convergence rate. It's will converge in polynomial in m steps. This is some numerical results. Comparing the QIS and GD, you can see that QIS is indeed faster than GD, and there are also but like if you run these algorithms, even for a system of 10 qubits using brute force exponential size matrix computation, it's very slow. You need to run this thousands of iterations to converge to for example to 10 to the minus 8. So the question is can you accelerate this iterative process? We've considered very interesting heuristics called Anderson mixing. It's a numerical heuristics for accelerating fixed point iteration algorithms, a very general algorithm. And it works for the case where you have iterative fixed point algorithm. So G, the trivial algorithm would be apply G over and over again, right? You would converge to the fixed point. But the Anderson mixing uses a history. So you do a iteration, and the second iteration uses the first update history information. It's impossible to digest what actually happens, but they are well-studied algorithms. In the linear case, it's actually corresponding to Jim-Ras algorithm for linear equation solving. And it works, the Anderson mixing works for the nonlinear case. This is what we found. If you apply this heuristics, Anderson mixing, you can, everything else is the same. The number of iterations will go from 1,000 to less than 10. So it's more than 2 orders of saving. It's very impressive, like when I see this result, that the classical tricks actually really works. And I found that when this algorithm would ever being used, maybe in quantum algorithm literature, you do some measurement about the Gibbs state and do some calculations. I believe that this classical heuristic must be considered very powerful. Okay, so to conclude, I've told you about both the forward and backward mapping problem from a convex analysis perspective, and we have give ways to relate the forward and backward mapping problem via QIS. But the forward problem, as I said, is a hard problem, right? But there are approximation methods, heuristic methods, such as Lie propagation, Markov decomposition, or mean field methods that are known. So maybe combining the heuristics for the forward problem and the acceleration methods, such as Anderson mixing, would give you heuristic methods for the backward problem. And in some sense, this method, algorithms are much easier to implement than the theoretically driven algorithms that we know. So I believe that maybe that's something that was considered. But in literature, like we don't have a very good heuristic analysis of how good this quantum versions actually work. There's only maybe one on the chain. We have a lot of good results. Can we generalize this to trees even? It's not quite clear. A theoretical problem that I found very interesting: what is the complexity of proximate quantum counting? For them, is it as hard as classical, or is it sharply hard? I think we still don't know. Another direction, I don't know, maybe it's possible to flip direction. Currently, the talk I gave is you can solve backward by forward direction. Can you flip the direction, and can you solve the forward can you approximate partition functions by solving Hamiltonian learning algorithms problems? Right? That's maybe another interesting thing to consider. So that's all for my talk. Thank you for attention.
Questions? I have one for starting. So about this complexity of approximating the quantum counting, do you have any conjecture? Like, what do you think?
I didn't spend much time, but I would consider it would be not similar to the classical case, right? I haven't like all these different directions you can look. The quantum case is messier and not as clean as classical, but in the end, it turns out to be similar. It's my impression, but don't take it for granted.
Very interesting talk. I have a perhaps naive question. So in condensed matter physics, you have like exactly solvable models like the Lieb-Linigo model. So does the formalism that you presented here cover these models? And if it does, can we learn something by you know, like testing your proposed methods on these models?
I don't know the model you mentioned, but I think that they would be a very good candidate for evaluating the performance, because in the executable models, you would know what things would work, what the expectations are. Right?
Yeah, so basically like, okay, what happens if you can calculate your free energy analytically? That's my question. If you have a model where you can do that.
I guess it would be a benchmark for how well this method will work, because the algorithms that we would use would be a heuristic, and you can compare the result with the exactly solvable result. Is my impression that maybe it's helpful to use it as an example to prove that this method works.
Yeah, so thank you very much for the very interesting talk. So maybe curiosity around the last point. So is this something that classically people know how to do? Because classically, as far as I know, the backward problem is in some sense well understood, right? So it doesn't go through this gradient descent. You can actually learn by just looking locally, right, at the behavior. And so I just wonder if classically this is actually useful.
I don't
for the
know,
fourth
actually.
point, yeah.
Yeah, I don't know. I haven't like. I think like the way to you can solve backward via forward is more natural, because you write down the equation, right? You can try like, okay, whether the equations are satisfied, but maybe you can try write down the equation in other way, but it's not natural, I guess. So that's. Or another thing that I don't know, and maybe I haven't spent much time digging the literature. What is the general result? Like if you have a mapping, like a continuous function mapping from Rn to Rn, you can have an oracle to compute the forward direction. What is the complexity of the inverse? Yeah, I don't know. Maybe it's known. Some numerical analysis literature, people know that kind of questions well, but I don't.
Any final question? If not, let's thank Zhengfeng again. But before I go, just that I have 4 reminders. Okay, no, 4 announcements. 2 reminders. One, that you have a picture now. So do you know where you're going to be? Okay, the photograph is coming, so we'll figure out where we're going. The second one is I have the business meeting at 12:30 here in this room. And there are 2 announcements. One, this is a smoke-free campus, so we should not smoke at all anywhere. Okay, so please respect that. And second, you should really follow the guidelines for the trash. So the volunteers, they need to, after like by the end of the day, they need to split bottles that are in the burnable trash and so on. So please do follow the guidelines and throw the cans, plastic bottles, and everything else in the burnable ones.